Assalamu alaikum. This is your Thermodynamics 2 class, and today is lecture number 19. Okay, so can anyone confirm what's appearing on my screen right now?
Yes, sir. Chapter 13/15 Chemical Reactions.
Okay, thank you so much. Okay, so now in the previous lecture we already discussed something about Brayton cycle and gas power cycle. Okay, so till now the courses of the Brayton cycle is till that topic which we already covered in the last class. Although there are two more topics, but if we have time at the end of semester, then we will look into it. That which is something related to how to increase the efficiency of Brayton cycle, similar to the Rankine cycle, which we discussed. That there is a regeneration process and there is other sort of process through which we can increase the thermal efficiency of the Rankine cycle. So similar way in the gas power cycle also there is two more topics. Okay, so but we will cover in the end of the semester. Okay, so now we will start new topics, which is chapter number 13 and chapter number 15. Okay, so which is related to the chemical reactions. Okay, so before this, we will discuss something about the quiz. Okay, so your quiz will be on tomorrow. Okay, so it is on LMS 28th. Okay, so this is the date which is shown in the snapshot. Okay, so you have this is your responsibility to enroll on LMS before this quiz. If you are not enrolled, okay, so you can I will give you the enrollment key. Okay, so you have to enroll it. So this is 28th May. It will start at 10 a.m. and end at 6 p.m. However, once you have clicked the quiz start, okay, it will just allow you 10 minutes to just submit that quiz. Okay, otherwise you will be marked 0 if you cannot submit it within 10 minutes. Okay, so this is related to vapor power cycle, Rankine cycle basically. Okay, it is very simple quiz. First 5 questions are MCQs. Okay, so which is a general type of MCQs, not very technique. Mean it was not related to numericals, any numerical. Okay, so it will be in, the topic that are included is Rankine cycle, actual Rankine cycle, reheat cycle, and yes, I think there are three topics over there. Okay, so and the last question, which is question number 6, is the short question. Okay, so in the short question, you have to specify only one word. Okay, and do not go for the story. Okay, so if you can read that statement, you can easily find that what is the suitable word as an answer. Okay, so be specific on that question because it is automatically tally that answer with the answer that is stored in the system. Okay, so that's why I do not go through the stories. Okay, so okay, enrollment key. You can, if anyone has didn't enroll yet on the Thermodynamics 2 class. Okay, so this is the enrollment key. So you have to note it down, and you can enroll before the start of that quiz. Okay, so if you have any question related to the quiz, you may ask. Otherwise, we can start with the lecture.
सर ये जो शॉर्ट क्वेश्चन है इसमें हमें एक टर्म लिखनी होगी बस
जी इसमें जस्ट एक वर्ड होगा that word you have to judge. Okay, what is the specific word as an answer you can select. Okay, but it is not related to the story. Okay, not related to story building question. Okay.
Okay.
Very simple quiz. Okay, so if you already attend all my lecture, I think if you cannot prepare, still you can easily achieve the highest marks in it because it is just a basic questions. Okay, which just is designed just like that, so that we can judge your understanding about the thermodynamics course related to the vapor power cycle. Okay, so now we will start a new topic, which is chapter 13. जी
रिकॉर्डिंग
अच्छा रिकॉर्डिंग ऑन नहीं हुई आपकी
सर ऑन है
हाँ रिकॉर्डिंग इज ऑन Okay, so now we will discuss the chapter 13, which is related to the gas mixture, some topics from chapter 13, and then remaining topic from chapter number 15. And this is only 2 to 3 lectures related to these two chapters. Okay, basically before these lecture, we already talked about many type of things related to the thermal efficiency, related to the gas power cycle, related to the steam power plants. But the important component in all these cycles are basically the combustion process. Okay, because if combustion take place, then there will be the possibility you can convert some energy into useful form of work. Okay, so that's why we have to cover this topic, because this is related to the combustion process that takes place inside your steam power plants or either inside your gas power plants. Okay, so starting from this one, which is chapter number 13. So far thermodynamic system involving a single pure substance such as water, homogeneous mixture of several pure substances like air, which we already studied in the previous lecture. So unlike air, which is a non-reacting gas mixture, but we have some applications where we have the reacting components. For example, in the combustion process. Okay, so the combustion basically is a combination of reacting components. Okay, so that's reacting components react together, and due to the chemical reaction, the combustions take place. The analysis of reacting mixture, that is mixture whose chemical composition changes during a process. So we will see that how to analyze these type of combustion process in this lecture. And when dealing with the non-reacting system, we already know that we have to consider several type of energy. Okay, so this is sensible internal energy, which is associated with the temperature and pressure, and latent internal energy, which is associated with the phase changes. Okay, and when we're dealing with the reacting system, specifically for the combustion process, so then the chemical internal energy, which is associated with the chemical energy, is also need to be considered. Okay, we can say it is a chemical bond. Okay, so now a non-reacting gas mixture can be treated as a pure substance, since it is usually a homogeneous mixture of different gases. Okay, because if you can see that when we are doing the combustion process, there is a fuel, there is the air, and air is a combination of different type of gases. And also, if for example you are doing the combustion process on methane, so for the actual methane, methane is basically the combination of many gases. It is not just one gas. Okay, so there is many gases involved in it. The property of the gas mixture depends upon the property of individual gas. Okay, so whatever the gas which composed that specific gas mixture, so we have to know the properties of individual component. Okay, and the amount of gas of each gas in the mixture. Generally speaking, it is possible to prepare table property for mixture. This has been done for a common mixture such as air. Okay, so we already have the thermodynamic properties of air. You already noticed that when we are analyzing the gas power cycle, we have to go to the properties table and find out some specific properties, that is the enthalpy, internal energy, or different sort of properties. But it is only available for air. Okay, but we have a range of different mixtures. Okay, so we can develop, but usually we have to follow some procedure in order to find these type of properties for different type of mixtures. Okay, those properties are not known to us from thermodynamic table. But it is not practical to prepare thermodynamic table, property table for every conceivable mixture composition. Okay, so this point I have already told that because air is because a common mixture, so that's why the air properties are known to us, but rest of other mixtures which are not common, so there is no need to develop the property table for each of the mixture composition. Therefore, there is a need to develop rule for determining the gas mixture and determining the mixture properties from knowledge of mixture composition and properties of individual components. Okay, so first the rule of ideal gas mixtures will be going through, followed by the real gas mixture. Okay, so these we can see that how we can determine the mixture properties. Okay, in the later slide. Okay, so from the chemistry knowledge, you already know that there are two terms while analyzing the chemical processes. One is the mass and one is the mole fraction. Okay, so mole is basically a unit to represent the number of atoms or number of molecules on a specific substance. Okay, so that is the unit for the analyzing the chemical compositions. Usually we use in the chemistry. Okay, so to determine the properties of mixture, knowledge of two things is required. So composition of the mixture, amount of each, so we already see. Okay, so there are two analysis which we have to perform while doing the combustion process. One is the molar analysis. So molar analysis basically by specifying the number of moles of each component. Okay, so in this case, for example, if there is a problem and there is specified that you have to perform molar analysis, so it means you have to find the mole fractions of individual components, or maybe you have to find the mole fraction of the mixture. Okay, so these are several type of things which we discuss in the later on. Okay, now there is a gravimetric analysis. So gravimetric analysis is by specifying the mass of each component. So if it is mentioned in the problem, you have to perform gravimetric analysis. So it's mean we are interested in finding the mass fraction rather than the mole fractions. Okay, so to elaborate the concept of mass and mole fraction, so we just consider a mixture that is composed of k components. So k components mean that, for example, there is a mixture of H2 and O2. Okay, and combined it will make some gas mixture. Okay, so for this we can say that we can represent the mass of the mixture, which is written over there. Okay, it is equal to summation of K, which is the K is basically a mixed component. Okay, so that component may be the H2 and maybe O2. Okay, and I is for specific component. Okay, so what we have to do is, if you have to find the mass of the mixture, just simply you have to add mass of H2 plus mass of O2. Okay, and you will get the mass of the mixture, which is shown over there, which is equal to 38 kg. Okay, so if we have 10 type of different components in the gas mixture, so we have to add all the masses of the individual component. So this is the meaning of this equation. Okay, so in the similar way, when we have to go for the mole, okay, so for the mole number, we either have to find the number of mole of the mixtures. Okay, so for example, if we have two gases H2 and O2, and the number of moles are given, which is 3 kilomole of H2 and 1 kilomole of O2. Okay, so we have to add all the number of moles of the individual component to get the number of mole of mixture. Okay, so this is the procedure. Okay, so we just have to add 3 plus 1 and we will get the number of mole of mixture. Okay, so now another term which we have to use to solve some problems in this chapter, the ratio of the mass of component to the mass of mixture is called mass fraction, and we denote it as MFI. Okay, so I denote the individual component. Okay, for example, I have to find the mass fraction of H2. So what I have to do is, I just have to take the mass of H2 and divide with the mass of mixture, which is the combined mass. Okay, and I will get the mass fraction for the individual component. And in the similar way, if we are more focused on the mole fraction, to finding the mole fraction, so we just have to find the number of mole of individual component and divide with the number of mole of mixture. Okay, so similar thing, for example, if we have to find the mole fraction of H2 in the gas mixture, so we have to find, we just have need number of moles of H2 and number of moles of mixture. Okay, and we will get the term which is Yi, and mole fraction we have to denote with the Y, small y. Okay, and I hope you already have seen these type of equations in the chemistry classes in your FSC, I think. Okay, so these are the same things that you already studied. Okay, but before analyzing a more difficult question, we have to go through these type of equations. Okay, so now there are two other terms. Okay, so which we can say that you already know that there is when we have to find the mass of the substance, which is equal to number of mole into molar mass. Okay, so in this equation, N is basically number of mole and M is basically the molar mass. Okay, and molar mass you can easily find for the gases in your thermodynamic table. Okay, so if you can go to thermodynamic table A1, so you can easily find there are molar masses are given over here. So if you are talking about air, here molar mass is given. So any gas which you are interested in for the analysis purpose, you can take that molar mass from table A1. Okay, so from here, because we are interested in to find the properties of the mixture, okay, so we can say that molar mass of the mixture is equal to mass of the mixture over number of mole of the mixture. Okay, so mass of the mixture we already discussed in the previous class, previous slide, sorry. So it will be summation of mass of individual component basically, and number of mole we can say just will be number of mole of the mixture. Okay, so we are trying to develop one equation which we can use for the further analysis. Okay, so we can say that okay, so for mi we can write mi is equal to number of mole of individual component and molar mass of individual component. So we can just put this term into this equation. Okay, so it will turn out to be summation of number of mole of individual component, molar mass of individual component over number of mole of mixture. Okay, so this is another form of molar mass of mixture equation. Okay, so from the previous slide, while talking with the mole fraction, we already know that y of y, mole fraction of individual component, is equal to number of mole of individual component over number of mole of mixture. Okay, so we can just replace this term with yi. Okay, so we can say summation of yi, and we can say it will be for k components. Okay, so k is any number of components. Okay, so yi and mi. Okay, so now this is the equation which we developed to find the molar mass of the mixture. Okay, and for the mixture molar mass, we can sometimes say that it is the average molar mass, or we also say it is the apparent molar mass of the mixture. Okay, so if in the question it is mentioned you have to find the average molar mass, so it's mean that we have to find the molar mass of mixture. Okay, so for this you need mole fraction of the individual component and molar mass of individual component, so you can easily find the molar mass of the mixture. Okay, so now here's another term which we are interested in, because if you can remember that while analyzing the gas power cycle, most of the time we use the gas constant, which is the R. Okay, so R is basically specified for every gases. Okay, so if there is air, so its R value is different. If it is methane, its R value is different. Okay, but now if we have the mixture of the gases, okay, so then we can denote that gas constant with Rm. Okay, so basically Rm is the gas constant for mixture, and it is basically Ru, which is Ru is basically the universal gas constant, and we have to divide with the molar mass of the mixture, which we get from this equation. Okay, so Ru value you can easily find in the thermodynamic table A1. Okay, so if you can okay, so here it is mentioned over there, if you can just take a look of it. Okay, so this is R, which is the gas constant, which is equal to Ru over Mi, and Ru value is 8.31447 kilojoule per kilomole dot Kelvin. Okay, so either you have to remember it or you can just find out this value in the table A1. Okay, because in the paper these tables are allowed to you, so you do not need to remember it also. Okay, so from here we have to develop another term which we already discussed, that mass fraction of the individual component is equal to mass of individual component over mass of mixture. Okay, so this equation we already seen in the previous slide as well. Okay, so from here if we can just put the value m is equal to nm in this equation, so we can write that mass fraction of individual component is equal to number of mole of individual component, molar mass of individual component, or number of mole of mixture, molar mass of mixture. Okay, and from here we can just say that Ni, number of mole of individual component, over number of mole of mixture is equal to Y. Okay, and from this we can say that Yi is equal to molar mass of individual component over molar mass of mixture. Okay, so this is the equation for the finding mass fraction of the individual component. Okay, so this depends upon the data which is available in your problem statement. So either you have to use this or you can use this directly also. So this we can find while solving the problems. Okay, so if you have any question, you can ask me or you can note it down, and then we'll move towards the next part.
इसने ये नंबर ऑफ मोल्स से इसीलिए मल्टीप्लाई किया ना ताकि हमारे मोल्स के मुताबिक मैथ आ जाए।
क्या चीज़ आप पूछ रहे हैं मुझसे?
सर मैं इसका पूछ रहा हूँ जो फाइनल स्टेप में हमने नंबर ऑफ मोल्स भी मल्टीप्लाई किया मैथ्स के साथ, इसकी वजह यही है ना कि हमारे अगर मोल्स
ये इस टर्म में?
जी सर।
अच्छा, ये तो हमने यहाँ से लिया mass of the substance। ये तो आपकी केमिस्ट्री नॉलेज है कि mass of substance is equal to number of mole into molar mass। Okay, so if you are interested to find the mass of the substance, we can easily find from this equation. So this is the basic equation from chemistry.
ओके सर।
Okay, so these all equations which we already discussed are mentioned in the slide as well. So you have to go through this by yourself because we already discussed, and this is your topic 13-1 from your book. Okay, so either you can follow that topic. Okay, so that you will get better understanding what are the meaning of these all equations. Okay, so now coming towards one question. Okay, so first you have to read the statement, then we will try to solve it. Okay, basically this is example 13-1 from your book. Okay, so consider a gas mixture that consists of 3 kg of O2, 5 kg of N2, 12 kg of CH4, okay, which is shown in the figure as well, that your gas mixture, okay, for example this is a container, and the gas mixture inside this container consists of these three gases. Okay, so we have to determine the mass fraction of each component, or B part we have to find the mole fraction of each component, and C part the average molar mass. Okay, so average molar mass basically molar mass of the mixture. Okay, and gas constant of the mixture we have to find. Okay, so you have to note down the statement and we will go forward for the solution. Okay, so now coming towards the solution. Okay, so in the part A, we have to find the mole fraction of the individual component. Okay, so for mole fraction, we already know that so yi is equal to ni over nm. Okay, so in the question it is mentioned that the masses. Okay, so there is no number of moles are given in the question. Okay, so first thing we have to find the number of mole of okay, sorry, so first part is to find the mass fraction, sorry. Okay, so this is the second part. Okay, so in the first part simply we need the mass of the mixture. So mass of the mixture is basically the combination of mass of individual components. So mass of O2 plus mass of N2 plus mass of CH4. Okay, so there are three gases. So first we need to add these three values, 3 plus 5 plus 12, which is mentioned in your problem statement, which is equal to 20 kg. Okay, and now we can easily find the mass fraction of individual components. So for example, if we have to find mass fraction of O2, simply we use mass of O2 over mass of mixture. Okay, so mass of O2 is 3 and mass of mixture is 20. Okay, you just take the ratio of these two terms, so you will get 0.15. Okay, so similar way, mass fraction of N2, which is equal to mass of N2 over mass of mixture, and which is equal to 5 over 20. Okay, and from this we can easily say it will be equal to 0.25. Similar procedure, mass fraction of CH4, which is equal to mass of CH4 over mass of mixture. Mass of CH4 is 12 and mass of mixture is 20, and if you take the ratio, it will be equal to 0.60 of the mass fraction. Okay, so you can also say that the mixture consists of 15% of O2, 25% of N2, and 60% of CH4. Okay, in the combined in the insulated tank, or you can say it will be the mixture composed of these mass fractions. Okay, so you have to note it down and move towards the part B. Okay, so in the part number B, we are interested to find the mole fraction. Okay, so mole fraction of individual component is equal to number of mole of individual component over number of mole of mixture. Okay, so first we have to find the number of mole of individual component. Okay, so number of mole of individual component, for example, number of mole of O2 is equal to mass of O2 over molar mass of O2. Okay, so molar mass of O2, you can easily go to thermodynamic table A1 if you do not remember it. Okay, so you can easily find the molar mass from that table. Okay, the 3 kg of mass of O2 and 32 kg per kilomole of molar mass. Okay, if you can just divide it, it will be equal to 0.094 kilomole. So similar thing, you have to find the number of mole of individual component for N2, so which is equal to mass of N2 over molar mass of N2. So mass of N2 is 5 kg and molar mass of N2 is 28 kg per kilomole. Okay, if you can just take the division, you will get 0.179 kilomole. So number of mole of CH4, which is equal to mass of CH4 over molar mass of CH4, which is equal to 12 kg of mass of CH4 and molar mass of CH4 is 16 kg per kilomole. It will be equal to 0.750 kilomole. Okay, so now these are the mole numbers of individual gases. Okay, so now we will easily find the number of mole of mixture. Okay, so you just have to add number of mole of O2, number of mole of N2, number of mole of CH4. So you will easily find the number of mole of mixture. Okay, so it will be equal to 1.023 kilomole by just addition of these three terms. Okay, so our main target is to find the mole fractions. Okay, so for mole fraction of individual component, which is O2, so simply you have to divide number of mole of O2 over number of mole of mixture. So number of mole of O2 is 0.094 and number of mole of mixture is 1.023, and it will be equal to 0.092, and number of mole of N2, which is equal to number of mole of N2 over number of mole of mixture. Okay, so the mole fraction for N2 becomes 0.179 over 1.023, and if you can just divide it, it will be equal to 0.175. And similar procedure y of mole fraction of CH4, which is equal to number of mole of CH4 over number of mole of mixture, and if you can just take the ratio of these two terms, 0.75 over 1.023, it turns out to be 0.733. Okay, so this is the part number B, where we have to find the mole fraction. Okay, so this is basically the molar analysis. So part A is basically the gravimetric analysis. Okay, so in which we have find the mass fraction. Okay, so in this part B, we have find the mole fraction. So this is the molar basis. Okay, so you have to note it down, then move towards the next part. Okay, so now coming towards part C, so in which we have to find the average molar mass of the mixture. Okay, so average molar mass of the mixture, you already know that capital M and small m denote the mixture, which is equal to mass of the mixture over number of mole of mixture. Okay, so we already have both of these terms. Okay, so 20 kg is mass of the mixture and number of mole of mixture is 1.023. Okay, so if you can just take the division, it will be equal to 19.6 kilomole. Okay, so this is the solution for this part number C. Okay, and part number C, the molar mass of mixture, we can also find another from another relation. So, or you can use, okay, the relation molar mass of mixture is equal to summation of yi, which is mole fraction, into molar mass of individual component. Okay, so you already know that if you can just add these terms, you will get the molar mass of the mixture, which we see in the previous slide as well. So molar mass of O2 plus y of N2, molar mass of N2 plus mole fraction of CH4 and molar mass of CH4. Okay, so you have already these terms with us, okay, from the previous part B, and this you can easily find from thermodynamic table. So if in the question where the data is available in this term, okay, so you can either use this equation to find the molar mass of the mixture. Okay, so the last thing which is required in this question is to find the gas constant for the mixture. Okay, so gas constant of the mixture basically uh, Ru over molar mass of mixture. Okay, so Ru value you can find from table A1, which is 8.314. You can say kilojoule per kilomole dot Kelvin, and molar mass of the mixture you already get, which is equal to 19.6 kilomole. And from the solution you will get 0.424 kilojoule per kg dot Kelvin. Okay, so this is the solution for part number C. So now the solution is completed. So if you have any question, you can ask me. Then we'll move towards the next question. so we will take I think 10 minutes break, and then we will join back after 10. Okay, so now coming towards another question, which is from your book 13-10, it is, I think. Okay, so first you have to read the statement. The composition of moist air is given on a molar basis to be 78% N2, 20% O2, 2% H2O. Determine the mass fraction of the components of the air. Okay, so it's mean we are. Okay, so it's mean that we are interested to find the mass fraction of the individual components. Okay, so because it is mentioned that we have to find the mass fraction. Okay, so first thing is that it is mentioned that it is a moist air. Okay, so basically moist air is composed of many other different gases as well. Okay, but there are many small amount of, for example, there's neon as well, and there's other gases as well. Okay, so the amount is very small, so that's why we have to ignore it, and we just say that it is a dry air, and we assume that it consists of nitrogen, oxygen, and some portion of water vapor. Okay, so now coming towards the part for the solution. Okay, so we already developed one relation which is mass fraction of individual component is equal to mass of individual component over mass of mixture. Okay, because this is 78%, 20%, and 2% is basically the value of y, which is the mole fractions. Okay, because it is mentioned it is a molar basis on a molar basis. So y is known to us for all the individual components. Okay, so we already see that there is one relation through which we can easily find the mass fraction, which is a function of. Okay, so from here we can say that it is Ni over Mi, similar number of mole of mixture, molar mass of mixture, and we replace this with the Yi, which is the mole fraction of the individual component. So molar mass of individual component we can easily get from the thermodynamic table, and molar of mass of the mixture we also easily find out. Okay, so first thing we can do to find the molar mass of the mixture, because this we directly get from the thermodynamic table. Okay, so the molar mass of the mixture also we can easily get. So we just place with the small m. Okay, so summation of yi and mi. Okay, so we already know that if we can just multiply 0.78, which is the mole fraction for the first gas, which is N2, and molar mass of N2 is 28. Okay, so similarly you have to add it, the mole fraction of O2, which is 0.2, and molar mass of O2, which is 32, and plus mole fraction of H2O, which is 0.02, and molar mass of H2O, which is equal to 18. Okay, and if you can just add these all values, it will be equal to 28.6 kg per kilomole. Okay, so this is the molar mass of the mixture of moisture. Okay, so now we have the molar mass of the mixture, so we can directly use this relation, which is the molar mass of the individual component. Okay, so we, for example, we have to find the molar mass of N2. So we can just multiply 0.78, which is the molar, which is the mole fractions of N2, and molar mass of N2 is 28, and molar mass of the air is 28.6. Okay, so from here we can just say it will be equal to 0.764 if we can just solve it. So in the similar procedure, molar mass of second gas, which is O2, 0.20 mole fraction, 32.0 molar mass of O2, and molar mass of mixture is 28.6. So if you can just solve it, it will be equal to 0.224. Okay, so in the similar procedure, you can easily find the mass fraction of H2. Okay, so simply you have to multiply the term 0.02 with the molar mass of H2, which is 18, and the molar mass of air, which is 28.6, and you can solve it. You will get 0.013 of the mass fraction for H2. Okay, so all the three required things are known to us, okay, which is required from the question. Let's mean we the mass fraction over moist air is composed of 76.4% of mass fraction of air, 22.4% of O2, and 1.3% of H2. Okay, so if you have any question, you can ask me and you can note it down. Then we will move to the next part. Next question. Okay, so coming toward the next question. So this is 13-11 from your book. Okay, so it is mentioned that a gas mixture has a following composition on a mole basis. Okay, so 60%, so it's mean that it consists of 60% on a mole basis of N2 and 40% of CO2. And determine the gravimetric analysis of the mixture. So it's mean you have to find the mass fractions. Okay, because it is clearly mentioned that there is a gravimetric analysis you have to perform. Its molar mass and gas constant. So you have to note it down and we move to the solution. Okay, so now from the solution, first from the problem statement, it is mentioned it is 60% of N2 and 40% of CO2 on a mole basis. So first thing you have to consider that your total number of mole for the mixture is 100 kilomole, okay, and in which 60 kilomole is for N2 and 40 kilomole of CO2. Okay, so this is just for consideration, or you can just say it will be for the assumption that you can choose that it is 60 kilomole of N2 and 40 kilomole of CO2, so that we can solve it easily. Okay, so by using this, first thing is to for the mass fraction. Okay, because we have to find the gravimetric analysis. Okay, so we need two things, which is mass of the mixture and the mass of the individual component. Okay, because we do not have any value in the problem statement. Okay, so first thing is you have to find the mass of the individual component. So mass of N2 is equal to number of mole of N2 into molar mass of N2. Okay, so if you can multiply these two terms, which is 60 kilomole and molar mass of N2 is 28 kg per kilomole. Okay, so if you can just multiply these two terms, it will be equal to 1680 kg. Okay, so in a similar way, you have to find the mass of CO2. And molar mass of CO2. Okay, so here you have to multiply 40 and which is the number of mole of CO2, and MCO2 is 44. Okay, so you will get from thermodynamic table and it will be equal to 1760 kg. Okay, so from here we can easily find mass of the mixture, which is equal to mass of N2 plus mass of CO2. And if you can just add these two, 1680 plus 1760 turns out to be equal to 3440 kg for the mass of the mixture. Okay, so now we have both of these terms, so we can easily find the mass fraction of the individual component. So mass fraction of N2, which is equal to mass of N2 over mass of mixture. So here we can just divide 1680 with 3440, it will be equal to 0.488, or you can say it will be 48.8%. Similarly, mass of fraction of CO2, it will be equal to mass of CO2 over mass of mixture. Mass of CO2 1760 or mass of mixture is 3440. It will be equal to 0.512, or you can say 51.2% of the mass fraction of CO2. Okay, so this is the first solution. Then you have to note it down and move towards the next part, which is the average molar mass of the mixture. So now the molar mass of the mixture, which is equal to mass of mixture over number of mole of mixture. Okay, so we have both of these terms with us. First one is 3440 and 100 kilomole, which we already considered. Your gas mixture consists of 60 kilomole of N2 and 40 kilomole of CO2. Okay, so from here we can easily find the molar mass of the mixture, which is equal to 34.40 kilogram per kilomole. Okay, now another required thing is to find the gas constant for the mixture. So the gas constant of the mixture is equal to universal gas constant over molar mass of the mixture. Universal gas constant value is 8.314. You will get from thermodynamic table A1 kilomole dot Kelvin over mass of the mixture is 34.40, which we already found in the previous step. So it will be equal to 0.242 kilojoule per kg dot Kelvin. Okay, so this is the required solution for this problem. Okay, so if you have any question, you can ask them, or you can note it down, then move towards the next question. So another question from chapter 13, which is 13-3 example. Okay, so you have to read the statement. So it is mentioned that there is an insulated tank which is divided into two parts. Okay, so two compartments. So first contain O2 and other one is contain N2. Okay, so the value of the masses are given 7 kg of oxygen and at 40 degrees Celsius and 100 kilopascal, which is the O2, and the other compartment contains 4 kg of nitrogen at the temperature and at pressure. Now the partition is removed and the two gases are allowed to mix. Okay, so now it's become a mixture. So you have to determine the mixture temperature and you have to find the mixture pressure after equilibrium has been established. Okay, so this is the required thing which we have to find. So you have to note down the data and move towards the solution. Okay, so now starting from the solution, so it is mentioned in the part A, we have to find the mixture temperature. Okay, so in order to find the mixture temperature, what we have to do is we have to apply the energy balance equation for this insulated tank. Okay, so it is mentioned it is an insulated tank, so it means that there is no energy transfer to or from the system. Okay, so in the part number A, we can say by applying the energy balance that energy in minus energy out is equal to change in energy. Okay, as there is insulated tank, so this term will automatically 0 and we can say that delta U is equal to 0. Okay, so why we choose internal energy? Because if you can notice, it is insulated tank. Okay, there is no movement of working fluid from one place to another. Okay, so that's why we can represent with the change in internal energy. If there is a piping component, for example in the case of steam power plants or previous example which we already see, so there where there will be a working fluid transfer from through the piping component, so that's why we use delta H. Okay, so from this we can represent with the delta U, and delta U here we can choose internal energy for the individual component. So there's two gases, so internal energy of O2 plus change in internal energy of N2 and it is equal to 0. Okay, so now you already know from the previous thermodynamic 1 also and in the previous lecture knowledge that delta U is equal to M Cp delta T, and if it is delta H it will be equal to M Cp delta T. If you want to find the delta H, you can also find, because if you can notice that delta H is equal to delta U plus PV. Okay, so in this term, PV is basically the work. Okay, so that work which we require to move the working fluid from one place to another. Okay, so from this equation we can say that delta U is also equal to delta H, because this is 0 in this type of question for the insulated tank. Okay, so this you have to analyze by yourself, that if it is not mentioned which equation you have to use, so you can use any type of equation, but you have to provide some clear statement that why you have to use this assumption. Okay, so now here we can replace this delta U with mCv delta T, and we can say mCv final temperature, which is the mixture temperature, because if we have two different mixtures at different temperature, so final mixture is basically final temperature is basically the temperature of the mixture. Okay, so once these two mixtures are mixed together, and T1 is the initial temperature which is mentioned in your question. Okay, so this we can just say it will be N2, and delta U for N2 is equal to mCv final temperature for both of these mixtures are same, and T1 is the initial temperature which is mentioned in your problem statement, that is equal to O2 and it equal to 0. Okay, so this is the mass which is given in your question, and the mass of O2 is 7 kg and mass of N2 is 4 kg. Okay, and CV and CP value, CV value, you can easily go to your, okay, so you have to go to table A2, okay, and you can easily find the value of CV for N2, which is equal to 0.743 kilojoule per kg dot Kelvin, and also you can find the CV value for O2, which is equal to 0.658 kilojoule per kg dot Kelvin. Okay, so this comes from table A2. Okay, so now just plug in the value in this equation, which is MCV Tm minus T1. Okay, so this equation becomes 4 kg of N2. CV value for N2 is 0.743. Tm value we have to find. T1 value is mentioned in the question, which is 20 degrees Celsius. Plus 7 kg. And CV value of O2 is 0.658. And from here you can get Tm, which is unknown to us, and T1 value is 40 degrees Celsius. Is equal to 0. Okay, either you can convert this into Kelvin also. Okay, and if you can just solve for Tm this equation, you will get the value of 32.2 degrees Celsius. Okay, so this is the first thing which is required for part number A, to find the mixture temperature. Okay, so this is the solution for part A. If you have any question, you can ask me. Then we move towards the next part. So now in the part number B, the required thing is to find the mixture pressure. Okay, so for mixture pressure we can use with the ideal gas relation. So we already know that PV is equal to mRT. Okay, so from here this R is basically the gas constant for the mixture here. Okay, so we can replace with the another term. We already know that mixture. Okay, and we can first say that because we are interested in to find the pressure of mixture, so Pm Vm is equal to mm Rm and Tm. Okay, so this term we have to find. Okay, so Rm is equal to universal gas constant over molar mass of the mixture, and mass of the mixture is equal to number of mole of mixture into molar mass of the mixture, which we already see in the. Okay, so these two terms we have to use and plug in these values into ideal gas relation. Okay, so now here we can develop one relation which is Pm Nm mm Ru over mm or Tm. Okay, so from here we can just eliminate this molar mass of mixture term, and we can say Pm Vm is equal to number of mole of mixture, universal gas constant, and temperature of the mixture. Okay, so this is the relation which we have to use to find the pressure of the mixture. So in this question, we do not have the value of Nm with us. Ru value we can easily go to table A1, we can find it, and Tm value we have already found in the part A. Pm value is also unknown to us. Okay, so first we have to find the number of mole of individual component. So number of mole of O2 is equal to mass of O2 over molar mass of O2. So mass of O2 is known to us from the question 7 kg and molar mass of O2 is 32 kg per kilomole. Okay, so if you can just divide these two terms, it will be equal to 0.219 kilomole. So similar thing, number of mole of second gas which is N2 is equal to mass of N2 over molar mass of N2, and it turns out to be equal to 4 kg, which comes from problem statement, and which is equal to 28 kg per kilomole for N2, and if we can solve it, it will be equal to 0.143 kilomole. Okay, so now from here we can easily find the number of mole of mixture by just adding these two terms, number of mole of O2 plus number of mole of N2, and it turns out to be 0.219 and plus 0.142, and it is equal to 0.362 kilomole. Okay, so now we have one term which is unknown to us, number of mole of mixture. Okay, so you have to note it down and move towards the next part. Okay, so now we need the value of Vm in this equation. What is the volume of the mixture? Okay, so first thing is you need the volume of individual components. So volume of O2, which is equal to, from the ideal gas relation, number of mole Ru T1 over P1. Okay, so just by using the ideal gas relation, we develop one equation. Okay, so number of mole of the O2 is known to us from the previous part, on previous slide. Okay, so which we say that it will be equal to 0.219, and R of U, which is equal to 8.314, and T1 is 313 Kelvin, which is mentioned in your question. And P1 is also mentioned in the question, which is 100 kilopascal for the O2. Okay, so if you can just solve it, you will get 5.70 meter cube. So in the similar way, you have to find the volume of N2, and you will have to use the same relation, okay, by just replacing the values for N2. Okay, so here we have to use the number of mole for N2, which is 0.143 kilomoles, 8.314 universal gas constant, and 293 Kelvin, and divided by pressure of the N2, which is 150 kilopascal. And if you can solve it, you will get the value which is equal to 2.32 meter cube. Okay, so here we can easily find the volume of mixture, which is equal to volume of O2 plus volume of N2, which is equal to 5.7 plus 2.32, and it turns out to be equal to 8.02 meter cube. Okay, so we have all the term with us: Vm value, Nm value, Ru value, Tm value. So from here we can easily find the value of mixture pressure, which is equal to Nm Ru Tm over Vm, and we just plug the value 0.362 kilomole for the mixture. Ru value is 8.314, and temperature of mixture come from the part A, which is 305.2 Kelvin, and volume of the mixture is equal to 8.02 meter cube. Okay, and if you can solve it, you will get 114.5 kilopascal. Okay, so this is the pressure of mixture which is required to your problem, so that you have to find. Okay, so now solution is complete. If you have any question, you can ask me, or you have to note down the solution. Okay, so we can stop at this point. Okay, so you have to solve one question by yourself. So only you have to change some values. So here we can change this value as 10 kg and this value as 6 kg, and you can replace this as 200 kilopascal, and this will be equal to 350 kilopascal. Okay, so you have to solve this question again by using these values, and you have to determine the maximum temperature and mixture pressure of equilibrium. So again, all the students will get 0.2 absolute marks for this. Okay, so again I have to announce one thing. Okay, so because as per the new mark distribution of your final and your midterm evaluation, there is 20% will be given to the assignments and 10% will be given to quiz. Okay, so the quiz that we already on the coming Friday. Okay, so tomorrow. Okay, so one quiz and one quiz maybe in the next week. Okay, so there will be two quizzes total and there will be four assignment. Okay, so already I have taken three assignment from you. Okay, so the last assignment, which is the fourth assignment, which I will decide at whatever the question I have assigned at the end, that will collectively called as a assignment 4. Okay, and the marks of this assignment is basically absolute 6. Okay, so all the students who have already sent it to me these questions which I assign at the end will straightforward get 6 marks. Okay, and for all the students who already submit in the clear way, not for the student who have just sent it to me the answer and send it to me the snapshot of the solution manual or anything like this from copy from the other. Okay, so the 6 mark is the absolute mark which you can lose if you are not going to submit the assignment, because I have noticed many students who have not sent it to me even one question. Okay, so that will be difficult for them to get this 6 marks. Okay, so take it seriously, and all of students who have not sent it to me, I will give still more 15 days. Okay, so you can send it to me, you can go through my lectures of the recorded session, and you can find it out in the end of each lecture and send it to me all the question. by, and you will get 15 days from this day. Okay, so if you have any question, you can ask me, and then I will just close this lecture.
सर तो इसके 3 टॉपिक्स यही है ना, रैंकाइन साइकिल, रीहीट रैंकाइन साइकिल एंड रीजनरेटिव रैंकाइन साइकिल।
रीजनरेटिव के ऊपर क्वेश्चन आई थिंक नहीं है इसमें, मे बी मैंने सेक्शन दूसरे सेक्शन को दिया था, लेकिन जो है ना इसमें रैंकाइन, एक्चुअल रैंकाइन और रीहीट साइकिल, ओके, ये तो इंक्लूडेड है।
ओके।
Okay, so I will show the slide of the quiz again, okay, so that you can remember that it will start from 10 a.m. from 6 p.m. on Friday. Okay, so you are only is allowed for the first only one attempt. Okay, so you have to take it, read the statement properly, and you can easily judge the answer. Okay, there will be no difficulty, and time limit is 10 minutes. Okay, so there is no time for the copy paste purpose. Okay, if you can just look into the copy paste, then you can just use this quiz.